The beauty of stoichiometry comes in when we begin planning and conceptualizing chemical reactions. If we want to run chemical reactions with a minimum amount of waste or as efficiently as possible, we need to appreciate the mass ratios that compounds combine in and use those to our advantage. So I want to talk in this video about the general kinds of problems that you'll see related to reaction planning and work through an example that we're going to continue through to get into some of the finer details of planning chemical reactions and using stoichiometry to do so. So, when planning and executing a chemical reaction, we use stoichiometry to answer some key questions. How much of each reactant should we use in terms of a mass or a solution volume? How much product should we expect? Given the amounts of reactants we started with and the amount of product we ended up with, how well did we do? We can use stoichiometry to answer these questions. And remember the stoichiometry toolbox here. Molar mass, molarity, and molar ratios or mole-mole ratios are the three primary tools that we kind of put together to solve stoichiometry problems. It'll be up to you to lay out and understand how the pieces fit together to get to the quantity that a problem wants. But practice with these elements of the stoichiometry toolbox and you'll start to see patterns in problem types and that sort of thing. So let's look at one more example, the reaction of hydrogen gas with SiHCl3. This is a process involved in the purification of silicon for the preparation of silicon chips, for example. At one point in the purification of silicon, hydrogen gas reacts with gaseous SiHCl3. What mass of hydrogen gas is needed to completely consume 21.73 grams of SiHCl3? Okay, so what we're given here is a mass of SiHCl3, 21.73 grams. And our target is the mass of hydrogen gas needed to react completely with that SiHCl3. So we're living completely on the reactant side in this problem. I'm going to practice what I preach and immediately convert this mass of SiHCl3 into a number of moles of SiHCl3. Get myself into mole land. How do I do that? Well, I divide by the molar mass. I divide by the molar mass of SiHCl3 in grams per mole. And this turns out to be 134.4 grams per mole for SiHCl3. Doing this division, I arrive at a number of moles of 0.162 moles of SiHCl3. From here, I need to convert to moles of H2, and we know that now that we're in mole land, all we need to use is the molar ratio between the two components we're interested in to do this kind of conversion. So we want moles of H2 on top, so we'll multiply by the molar ratio of H2 to SiHCl3, which in this case is just 1 to 1. 1 mole of H2 reacts with 1 mole of SiHCl3 in this balanced chemical reaction. So that gets us to a moles of H2, which is simply numerically equal to the moles of SiHCl3, 0.162 moles. How do we now get back to the target mass? Well, we simply multiply by the molar mass of H2, which in this case is very easy to calculate. It's just 2.016 grams per mole. This multiplication gives us our target value, which is 0.326 grams of H2 gas. In the next video, we're going to look at what happens when we use an excess of hydrogen gas. We'll learn how to identify that an excess is being used, identify H2 as the reagent that's in excess, and learn how to determine the situation at the end of the reaction after the reaction has run its course.